Moving into our final week of sort of intro material in using R, we have covered data import, basic kind of programming skills, basic loops. We have looked at how to do basic data formatting, restructuring, reorganization, transposition, and now we're finally getting into sort of the nitty-gritty little programming details of that are a little more specific to certain use cases. So up to this point in the base material, we've been talking more about broadly useful kind of functions and libraries. Here we're going to get into strings. And strings are something that you're going to deal more with in the sort of core data science-y parts of this class. Also in terms of any work that you do related to text. So if you do open-ended responses, if you do things like surveys where you collect information on narrative feedback, where somebody uses words in order to explain themselves. If you're doing any sort of qualitative data collection, then in those cases you are going to end up with text data. We are also going to end up with text data in the data science context when you are doing web-based data queries. So if you're pulling down data from the internet in some way, you will probably end up with text data in a lot of cases. If you use Qualtrics, you will pull down a lot of text data in different ways. Not just in terms of participant responses that are text, but also things like the type of computer that the person was using, other details about them that are in a text format. We'll all come back that way. And if when we start doing API and web-based scraping, where you're actually pulling data down from online databases in order to create data sets, which is not too far off in the future now, you also deal 100% in text data. So this is a very important sort of foundational skill set that you will find more useful than you might initially think. If you ever do any sort of bibliographic data analysis, you will also use a lot of text data. Your project this week is actually about bibliographic data analysis, which really means trying to understand citations. So that is what you'll be doing this week. So what we're going to do today is go over a number of things that we taught that you looked at in the data camp exercises on string manipulation. I hope everybody did both the string manipulation data camp piece as well as regex1. As regex1 is a really valuable way to kind of peek under the hood as to what's happening with regular expressions when you use the rebus library. And part of the reason that's important is because the rebus library does not always act the way you think it should. There are certain situations when it will make decisions on your behalf that you don't necessarily realize it's making. And we'll walk through some examples of that today. The reason that that's a problem is because you can end up matching things that you don't intend to, and you can't figure out why, because it doesn't make any sense when you look at it. But we'll go through examples of that in a minute. I'm going to go through best practices for string formatting, number 1 in R. Up to this point, we've been using almost entirely double quotes, the double foxies. We're going to talk a little bit about what that's supposed to look like for consistency's sake. How to do that in base R, how to create strings, how to reformat strings using base R. We'll talk about stringy a little bit in terms of importing. Stringy also has a lot of formatting functions, but you're not going to really ever want to use most of them because they're wrapped in stringer, which is the dplyr tidyverse, the tidyverse package that is really best for string manipulation. Stringer is actually built on stringy, so stringy is in stringer as a way to improve upon those functions and put them within the philosophy and language of tidy. So that's part of what's going on. And finally, something you didn't do in the data camp, I don't think, is how to actually work with Magritter pipes in string manipulation. So everything in stringer, I mean, it is tidy, but we didn't necessarily ever actually practice much piping related to string manipulation. So we'll do a little bit of that today. In terms of how to actually represent strings, you should just get in the habit of always using the double foxies, the quote as a way, double quote as a way to represent strings. If your string has a double quote in it, however, you should flip. They mean exactly the same thing. If something's surrounded by double versus single quotes, that is still a string. It makes no difference. What changes, though, is how it interprets the special escape characters inside it. So, for example, if we go into R, I can create a string called quote, quote. I can put a string called quote, quote with a single quote in it. I can create a string called, but I can't create a string with a double quote in it. That thinks that I'm still typing. That's what that plus means. So the reason it thinks I'm still typing is because what this really interprets this as is open quote, close quote, open quote. So I'm going to have to hit escape to get out of that. And you see if I put in 4, it'll give me an error because now it sees 2 pairs of quotes. But the only way if I really want to use a quote is use an escape character, which in this case is a backslash. And remember, a backslash is the back and forward part of a slash is the top. So a backslash tilts backwards, tilts to the left. So this is a backslash double quote, and that's how we end up with a string that contains a quote in it. If I look at my string at this point, you can see literally what that looks like. But that's also why we use the right lines, which is not going to work because I don't have the right library, I don't think. Oh, no, it does. Which is why we use the right lines function. This actually shows you what this is interpreted as after it goes through the base R string processing engine. The base R string processing engine is super important because this is where confusion occurs with regular expressions. Because when you try to create regular expressions, you're going to have to go through this processor that does this kind of thing. So we'll talk more about that in a minute. But it's a common point where people start to make errors and have a hard time trying to diagnose why they happen. If your string has both quotes and single quotes in it, use double quotes and escape. You can actually use double quotes 100% of the time. You don't have to do this middle step right here, but that is pretty common practice. And if you see it, that's why it's happening. So examples, double quote, this is your default sentence. If you have single quotes, this is for if you need quotes. And here's the double example, double quote, this is if you need backslash double quote, and quotes. And note then, because this is surrounded by double quotes, that these single quotes are not escaped. Makes sense to everybody. Very foundational kind of string processing aspect here. Don't confuse these guys. These are quotes. These are called smart quotes. Smart quotes are not quotes. Smart quotes are actually Unicode characters, and you learned a little bit about Unicode. This is what happens if you type quotes into Word. Word will automatically convert your single quotes into smart quotes and will wrap the quotes around whatever you've typed. These are evil. This is a terrible, horrible, obnoxious programmer's thing. Because these are not quotes. These are symbols. This is like you just put an emoji right there. So if you copy-paste, and the reason I say this, if you copy-paste from Word into R, it probably won't work because the code will convert all of your regular straight quotes into smart quotes. This is essentially a smiley. Like, that is not a quote. Don't interpret that as a quote. Be very careful. This also sometimes happens when people do things like copy-paste from Word into a web browser, like when they create a web page. So that sometimes when you copy-paste code off of the internet, it actually has smart quotes in it instead of correct quotes, straight quotes. So if you ever copy-paste from the internet and it doesn't work and you're like, I'm getting weird errors about unseen characters and things, that's probably why. Because you often get smart quotes in code that shouldn't be there. I will also tell you this is a little minor nightmare in publishing. We have, when we published a paper in Psychological Methods, we had some single straight quotes in it. And the people copy-pasting into the final manuscript converted them all into smart quotes for some reason. So then if you copy-paste from the PDF, it would break. And we had to fight with the editorial staff for a long time to get that fixed. So these, just be on the lookout. Be aware that this happens. If you ever see a curly quote, it is not a quote. Again, this is an emoji. This is not a real quote. Base R's right lines, I just demonstrate, shows you what strings really look like. Just be aware that it's there. In terms of escape sequences, I just told you one. We have this backslash double quote, just becomes a quote. This gets real weird real quick. Backslash inside quotes becomes a single backslash. These are the ones you should really pay attention to. Backslash T is a tab and backslash N is a new line. You also have backslash single quote becomes a literal single quote and backslash 2 becomes a literal double quote. There's actually way more than that. I use this term here, and it's very important you know this term, literal. A literal refers to a special character that is converted or interpreted as literally what it is. So in regular expressions, for example, the dot is used to represent any character, but if you backslash dot, it means literally a dot. So that means it's a dot literal. So it's just another way to refer to it. So you can see the full list in R if you use question quotes. I'll show you real quick what that list is. This will show you all of the various special characters that occur in R. You see, again, tabs, backspaces, alerts, tabs, all sorts of things. You're never going to use any of those, most likely, but you do need to be aware they exist, so that if you backslash an F and it's not what you expected, if you look in here, you're like, oh, it's because that's a form feed for some reason, and that's not what I meant to do. So just be aware these are here if you're using backslashes as a place to check. You can use Unicode code charts. You, in the data camp lesson, I think made like a little smiley world symbol or something like that. That is not going to work in RStudio. RStudio does not interpret Unicode. Unicode characters still exist. You can see the raw Unicode formats, but you can't see what they represent. In the kind of data that we usually work with in kind of a social science context, we usually don't need Unicode. This is not going to be real important for you unless you're doing international data collection. So if you're collecting data in multiple countries simultaneously, especially in countries that don't use a Roman or Roman extended character set, like if you're collecting Chinese data, Russian data that's in Cyrillic, that kind of thing, languages that use alternate character sets, that's where you're going to start to need to use Unicode. So we're not going to really talk about it much in here because it's really for specific kinds of projects that are not super common for us. But you should be aware it exists. Number formatting, yeah. The way that you do it is you turn off smart quotes in Word. Yeah, so the problem will be that if you already have a document that has smart quotes on, it will still have smart quotes in it. I've turned off smart quotes in mine for that reason. Yeah, smart quotes are horrible. It's a horrible thing. You shouldn't use them. It's especially problematic if you ever try to copy paste things from like Word into Blackboard. For those that are TAing and teaching classes. That's why sometimes that will screw up, and why those quotes will sometimes not appear as quotes on some people's computers, but will on other people's. It's very annoying. So yeah, just don't use smart quotes. It's a much easier solution. I can tell you a lot more about why Word is annoying, but I'm not going to. All right. So very important for us here is number formatting. This is related to how you force output in order to have the right number of decimal places. And if you have ever worked in copy pasting from SPSS, you have faced this demon also. But fortunately, we can do this kind of formatting at a broad scale in R, so it is much easier than it is in the Excel context, where you have to copy paste and remove asterisks and move minuses around and all the nonsense that you have to end up doing. But you do have to know what the command is in order to make it happen. This base command of format is the base R format. The format is the base R command that will pre-specify. It's real weird. It's a really strange thing that doesn't work intuitively the way you think it should. What it does is it determines how many digits are needed to display the precision of the most precise thing in your variable, and then it uses the number of digits that you specify here based on that number to extrapolate out as to how many digits you want. That's not a thing anybody ever wants to happen. That's a silly thing to do. So I would not use format. I would, in fact, use format C. What format C does is uses C-style formatting. C-style formatting is formatting that makes sense. So what C-style formatting does is, for example, here, it says format the variable x in a float format with 2 digits after the decimal place. That's what you want formatting to do, usually, is to specify the number of decimals you want, so just do that. This is going to be a much more useful kind of approach. You will note, though, if you ever get feedback back from R and you see, like, it goes into scientific notation for some weird reason, or if it reports, if it cuts off at a certain number of numbers, like if you're working with really big numbers, this will happen sometimes. Numbers that have more than 7 digits before the decimal place, and you're like, why is it cutting off where it is? I don't understand. The reason is because by default, R always uses format, and R formats to the value of digits in your options. So there are actually a huge number of kind of under the hood options that exist in R. If I do, for example, get options digits, oh, wait, get options, sorry. Here we go. You will see that the default is actually 7. So this number is used for all number formatting. That can result in some weird kind of output sometimes. Actually, I'm not sure if it'll do it with whole numbers or not. Yeah. So you see what it's actually doing here is it's interpreting that precision to this 7 things. It's not, I mean, it is digits, but it's digits both before and after the decimal. So you end up with 1, 2, 3, 4, 5, 6, 8 here, because it rounded. So this is the 7 digits that it's referring to. So if this ever looks weird to you, like if you're getting back getting back numbers in formats you don't understand, then it's probably something related to your digit specification. You can change it by doing options digits. I always forget whether it's plural, equals something else. And you can see that'll do all sorts of weird things in terms of rounding. So I just respecified my default option, and that's what happened here. These options can be hard set, but usually they get reset whenever R restarts. There's a preference file somewhere where you can change the defaults, but I wouldn't do that. I'm going to change it back here just so this looks normal going forward. So yeah, that's how formatting works. I would only really worry about the normal digit formatting in terms of like if something looks strange. For your formatting, when you're doing things in tables, I would use format C. Okay, pasting. We've actually already talked about pasting a lot, so we're not going to talk about it in too much more detail. But basic pasting just converts whatever you give it to text, meaning you can give it non-text things, and it will coerce them to character vectors. And then it just sticks them together as a vector of strings. So sep tells you what goes in between the parameters, and collapse will basically its existence communicates that you want to collapse everything down into one if you're giving it a set of things. And it will also tell you what you want to put between them. Paste 0 is a variation on paste. It basically just gives you this sep equals nothing default. That's the only difference between the two. Paste 0 is a relatively recent addition to the base R. The common point of confusion once you start learning these two is between C and paste, especially in the context of string str_C, which is totally different. So what C stands for is actually combine. Sometimes you will see this referred to as concatenate, which makes it seem like it's a string thing, but it's not. C stands for combine, and what C does is it creates a new vector with multiple elements in it. So if you do C 1, 2, 3, it creates a vector with 3 elements in it. If I do paste 1, 2, 3, on the other hand, it creates a single string, 1 element with the values 1, 2, and 3. And then you can probably guess if I do paste 0, what's going to happen. I end up with no separation. Okay? So don't confuse these. When you know you need a specific kind of output for a specific parameter, it's real easy to flip those around when you're just starting. So just be aware, this is actually 3-element vector. This is a 1-element vector containing a string. Okay. Both of those are more, or rather, paste is more useful if you're not already using stringer. If you're already using stringer, then you would probably use another function, which we'll talk about in a minute. In terms of getting text documents into R, the easiest way is to import stringy and use STRI read lines. The reason for that is because you can use read_delim to pull in from reader to pull in text files, but you have to use a lot of random little options in order to make it work. Because it will try to interpret what your file is, and strings tend to have all sorts of tabs and spaces and commas and all sorts of randomness in them. So it's going to try to, by default, interpret all of that stuff for you, and it will almost universally do it wrong. So you can fight with the options in reader in using read_delim. You can do that. It will eventually work if you fight with it long enough. But this just by default says every line is a string imported a line at a time. So it's just a lot easier. It imports it as a vector of strings using a format that we haven't used before really, which is called a large character vector. What that really means is it's a vector of characters that is too large for R to handle in the normal way it handles character vectors. So that's not important most of the time, but there are certain situations where that will matter. We won't deal with values quite that big here, but it's good to know that it exists. STR is empty is really useful because it returns a logical vector of which lines are empty. So you can do things like, let's see an easy way to do this. If I create a vector of strings, yes. Gotta write this correctly. No. Blank. We're going to assign that to strings, and then we're going to run, I'm going to run library stringy because I don't have it in here right now. And then I do str is empty strings. We end up with a logical vector containing values where the string is empty. So the usefulness of that then is to filter by that value. And actually we're going to say empties gets this value. That's not going to be super useful, but we can do this and get all the values of everything that are not empty. So again, what I just did there is I created a vector using string is empty of trues and falses, which means that I can use that as a filtering tool. And then I subsetted strings by those values. And specifically by the inverse of those values. That's why I have that bang there, because that essentially means not empty, so this becomes true, true, false, true. Okay? Everybody see that? When you import text files, you're going to have a lot of blank lines in most cases. The kind of stuff that we do in here, including in your project, it's very common to have lots of blank emptiness in a text file. So that you can leave them there for a lot of operations, but what will start happening is that R will have to process all those empty lines, and sometimes there's a lot of empty lines. So if you have, 10,000 empty lines, then that's a lot of extra processing that you don't otherwise need to do. So subsetting like this is a good way to get that done, and then you can also do other things like length to figure out how many of these strings actually contain data. So that's a useful set of tools you can use. Okay, that is stringy. That's really all the stringy that I would recommend you use, to be honest. Stringer contains pretty much everything else you want. This is part of non-core tidyverse. So if you import tidyverse, you still need to import stringer in order to get access to the string functions. Really important to note this prefix, str underscore. That means you're using a stringer function. Everything in stringer, everything has str underscore. And the reason for that is really to distinguish it from a lot of very similar sounding functions in base R. So strPOS and str underscore POS, for example, are two different functions, and they act a little bit differently. So be aware that the underscore means you're talking about a stringer function. And I will go ahead and import it now, just so we have it. strc, which I mentioned earlier, replaces paste 0, because usually in the kind of things that we do, you don't want separation by default. That's, again, one of those things that's just part of base R, but in practice we usually don't need it. We usually specify sep equals quote quote when we use paste, so str underscore c just does that by default. Not a big deal, you just have to remember that it does that. Acts a little bit more like, it can act more like paste if you give it a sep parameter. So for example, str underscore c comma sep equals quote space quote will act like paste. So you can configure it the other way, it's just important to know the defaults. The major reason that you want to use str underscore c is how it handles missing values. It will actually not propagate missing values out. So if a piece, like if you have two strings and you want to combine them, if you use paste, it will, and one of those is empty, it's an NA, it will literally just shove an NA into your string. And like literally the word NA. Actually, let's try this. So I already have one set of strings with 4 values. I'm going to say strings. I'm actually going to replace it with an NA in this case. 3 gets an A. There we go. Make sure that worked. Okay. Then new string gets sure, yep, nope, and banana. All right. So now we have these two. If I paste these together, you will see what happened is that NA became part of the string. That is a stupid thing to do. That is not a thing that you would ever want to do. You would not want to propagate a missing value as part of a string when you add them together. That makes no sense at all. If you use str underscore c, however, you will see it actually returns not as a string containing NA, but as a literal missing value. So if you have, for example, two sets of participant responses, and what you want to do is stitch them together, then you probably don't want a literal NA in your new column. You probably want to say, oh wait, I'm missing one of the two responses, therefore this is a missing value. So you almost universally want STR_C with the kind of data that we work with. So that's the major difference. This is why I would recommend using STR_C. So you should be able then to understand what these guys do. One of the real advantages of paste and STR_C is that it will propagate single values to as many cases as it thinks you should have. So let's say, for example, we take nums C, what did I do here? It's, I typed that a weird way, 1 through 5, and then we do paste participants nums. Oh, not participants. I want the literal word participants. If I do this as paste 0, if I do this as strc, you will see again that strc and paste 0 work the same way. What they're doing in all three of these cases is recognizing, oh hey, there's currently 5 numbers inside nums. This is a vector of length 5 right here, integer vector. And then it's saying, well, wait, participants is 1, so I'm just going to copy that over and over again to all the different individual pieces. This is a really convenient way to make labels if you need to add labels for some purpose as a new variable. You will also do some really kind of weird stuff that can be useful in certain contexts. Like if we do 1 through 5 and 1 through 10, for example, it will actually automatically detect for you that this is a multiple of this, and it will repeat that vector for the second one. It even very helpfully will give you a warning message saying, well, wait a minute, this was not the right multiple, but it'll still do it if you don't give it equal things. So in this case, I gave it a vector of 5 values and a vector of 10 up above, and it said, oh, 5 divides into 10, no problem. It creates those numbers. You can see 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then 1 through 10 at the end. In this one, I have a 5 and a 12, so it tries, but then it's like, that didn't work out evenly, and it gives you a warning. If you use paste, do you think there's a warning? What do you think it does? Not big paste. Just silently gives you back output, and also also just leaves out values and doesn't tell you, because that's how base R works. So it still does the same thing. And again, if I wanted it to look identical, I'd probably want to use paste 0. I get the same string here. But the difference is that this gave me a warning and told me that's probably not what you meant to do, because stitching together a 5-value vector and a 12-value vector doesn't really make any sense. Okay? See the difference? So strc just is a good, again, gives you warning messages to let you know that you probably screwed something up, which when programming happens a lot. In terms of specific queries you can give to strings, these are all super useful. str_length tells you how long the string is. It is very different from length. Do not confuse these. Again, str_length gives you the number of characters in a string. Length gives you the number of elements in a vector. Those are different. Okay? So you can get both length and string length from a vector of strings. So that's why this is important. If I take length of, what did I call that string vector? Strings. That's easy. Length of strings is going to give me one value of 4, because this up here is a 4-element vector containing strings. However, if I use str length, then I get a 3, a 2, an NA, and a 5, representing the number of characters in each of those. So just don't confuse those. They're very similarly named. This is length of a vector. That's what length does, which means number of elements in a vector. str length gives you literally the number of characters in each. So this is STR length in our context is useful for things like counting how many characters did people use in their responses. That's how I usually end up using it. To see like as a proxy for things like motivation to type out a response, or just if you happen to want to know that information in order to figure out, for example, one thing that we did, for example, is create in projects like this, is create a histogram so that you can see all the string lengths and look for outliers to indicate people who really weren't trying to give you a response. So string length is a really useful tool you can use for that kind of thing. STR sub sub stands for subset, so this is subset of string. This is really similar to sub STR, which we've actually already used in here many weeks ago. But the advantage is this negative indexing. It allows you to count from the end of the string and not just the beginning. Extracts information based upon location within, that should be string, returning all characters between position start and end, and you can't go backwards. What does this first one return? What do I get out of this? Yep, we would substring, go to character set 2, go to character 3, and continue. What does this one do? E and F? C and F, yeah. So what it's doing is it's taking the -2 position, and then it's continuing to the -1 position. Always going forward, okay? Start at -2, which is the second from the end, and proceed to -1, which is the last character, okay? What about this one? What does this do?
B and C.
I'll actually show you because this is really a weird thing. B and C? And what did I give it? -5 and 3? Why does that work?
5 is the second. 2 and then 3.
Yes. So what's happening here is, again, these are literally positions, not counts. That's a really important part of understanding this function. Here, I'm saying go to the -5th position, so that's 5th from the end, and then go forward to the 3rd position. So since the 3rd position is in front of the -5, we get B and C. Okay? So these are not lengths, and that's a big difference in relation to the other function, in relation to sub-STR. These are not lengths, these are positions. What happens in this one? -3 and 3, what is that going to do? Not an error. Empty set. It's not going to give me an error because this string exists. There is a string to search in. But when it looks, it says, well, position -3, go forward to position 3. I don't have any of those things, so it returns you empty string. Not an NA. Very important. Missing values are going to start to become more important as we move forward. So we end up with a missing set in this context. What will this do? Down here. STR sub blank -2. I give you some hints here. Start defaults to 1, end defaults to -1. Yep. So we end up here with there's actually an invisible 1 right there, because that's the default parameter. So it starts at 1, A, and then proceeds to position -2, which is E, so we end up with A through E. Okay? That's why you can also do sub value, comma, number, close paren, because that basically means count from this position to the end, because the default here is -1. Okay? And just to show you. So the default is -1, so what this is really doing is going from position 3 to position -1, so we end up with 3rd to the end. Okay? So those are queries. Searches and pattern matching is where strings get really interesting. There are a whole bunch of functions for this, and you will probably need all of them in different ways once you start doing pattern matching work. STR detect is the most kind of foundational of these. What it does is it takes a regular expression in the form pattern, and it returns a logical vector if it's detected. So very simply, we can go to STR detect, ABC, let's actually go back to strings. Strings, there we go. And we can search for a Y. And it will give you back True if a Y is detected, false if a Y is not detected, and NA if you're looking at a missing value, because obviously that should not be false. Okay. We can also use regular expressions. What will that do? That does mean any character. Not very useful here. But what it's doing is it's detecting, does any character exist? In this case, yes, so true, true, NA, true. You would never get a false there. Unless, what? Empty string. So if the string was empty and not NA, you would get a false. Okay? Very important distinctions, because they can cause you a lot of headaches later. If you use, where we go, STR subset, that's a way to take only pieces of strings using this pattern. It basically just says subset this set of strings based on this existing pattern to return what I want. STR subset strings Y, and we end up with only the strings that contain Y. In the Unix language, this is a function called grep, if you ever see that term. So this is a way to subset in a larger text document based on pieces of it. The advantage to regular expressions as an engine is it is extremely fast. You can subset using regular expressions on a massive data set with tens of thousands of cases very, very fast. That is not true if you try to do things, if you try to do any other kind of algorithmic approach, like if you build a function that will look one character at a time to look for a Y, that kind of thing. Regular expressions will work much better, so you really want to be familiar with them. Important distinction. STR subset is used to subset vectors, but you want to filter on STR detect to subset tables. Okay? Or you could use the subset command if you weren't working in tidyverse. This is important, because in this one, we are specifically taking a subset of a vector. If you use STR subset inside of filter, it will not work, because this variable, this subset, won't exist inside the tuple. So, for example, in this case, if I had subsetted this, if I used STR subset, I only get back one value. And if I tried to filter on yes, that doesn't work. You can't do that. You have to filter on a set of logical values. So, don't confuse those. STR subset to subset a vector of strings, filter to subset tibbles. We also have a lot of variations on detect that do slightly different things. Extract is really useful, because it basically just returns whatever the match is. And STR match will do basically the same thing, except if you have captures specified, it will return the captures also in a matrix. We'll go through an example of that in just a second. STR count follows the same rules as STR detect, but returns an integer instead. It counts, so that's easy. STR view is kind of weird. So you probably in data camp got used to using STR view in order to kind of like check yourself, like to examine whether or not the particular pattern you were using was matching and what it was matching. It brought up like a little web page essentially to show you that. That requires additional packages that are not by default part of Stringer. If you want to use that in RStudio, you're going to have to install these two things, HTML tools and HTML widgets, in order to use view all. Or in order to use STR view. So if you want to do that, I'm never going to require you to STR view, because it's really a diagnostic tool as you're trying to figure out why your regular expressions are working or are not working. If you want to use those, you need to install .packages and then install HTML tools and HTML widgets to use it. So just as a warning. So extract and match we're going to spend some time on right now. So if we STR extract and we look at strings and we look at, well, I didn't replicate any characters. That was not good. I'll have to redo that. And we extract on Y, then it's going to return Y and NAs for all these things. Important piece of string extract is this will only pull back the first match. Okay? If I want to pull back all matches, I have to use STR extract all, and that's going to return a list instead of a vector. Okay? Now we have a list, and you can see components 1, 2, 3, and 4. and or lists 1, 2, 3, and 4, and you can see the subsets in each of those. Okay. So if I use match, instead of a vector, I get back a matrix. Remember our basic data types, right? So now instead of a vector, I have a matrix with 1 column and 4 rows. And if I use captures, I get additional columns for the captures. So hopefully you remember the idea of captures. Say I wanted to match the term yes. I could search for yes like that. But I only wanted to return the y. I could do that. Okay? The advantage to this is you can look for very complicated conditions, like where a set of conditions is true, but then only return back a specific piece of that. You're going to have a bunch of examples of this in the project. Because what you're going to be doing is things like, you're specifically going to be trying to take a citation, an APA-formatted citation, and extract pieces of it. So that means you have to develop decision rules for what you want to get. So let's, for example, right now step through what happens if you want to extract the year from a citation. How would you do that? You would have to think, well, according to APA 6 guidelines, what do years always look like? And in APA 6, years are always surrounded by parentheses. So we could easily search for 4 digits surrounded by parentheses. But we don't want those parentheses back. So we can capture just the digits. And in that case, you would then want to specifically look only at this second column in order to get back the data that you want. So I'll show you at the very end of this an example of how to do that in dplyr or in McGritter pipes. But that's the basic logic we're going to be using for a lot of captures. So if you have captures inside, the way you can think about it, using captures inside matches is a way to return just a specific targeted piece of information within a larger set of decision rules. So, and again, that example, years are always surrounded by parentheses, so look for 4 digits inside parentheses, but only return the 4 digits. That's the kind of logic you're using. Operations, things you can do with strings. STR Split is a useful way to take a string apart into its pieces. In most cases, you would be able to use separate for this in dplyr. In most of our cases, the situations that, as in a social science context, you would likely need this. But it is good to know that it exists because there are situations where that's not true, especially when you're taking multiple sets of strings that have different lengths. In those cases, you might want to use STR Split instead of separate. STR Replace basically just takes an existing string and replaces it with another, it takes a string, matches on a pattern, and replaces just the pattern with the final replacement. So if we just do STR Replace, and we're going to look for yes, and we're going to replace it with no. Now our first yes has converted into a no. This can result in kind of weird things if you're not paying attention. Let's replace any character. Why did that happen? First character only. So remember, the STR Replace only replaces the first match. So in this case, the first match to any character is universally the first character of the entire expression. If I want to do everything, I want to use STR Replace All, and that's what we end up with. Do notice that it is not recursive, in that after I replace the no is now off limits. I'm no longer searching inside the no I just replaced it with. So anything that is replaced is no longer part of the search string, which is good, because if that wasn't true, that would be a lot harder. So, difference between STR Replace and STR Replace All. We have STR Trim, which is also real useful. I'm not going to demonstrate it. What Trim does is very similar to Trim WS, which we've used before. It just trims white space. That means extra tabs, new line characters, and spaces on the outside of a string. By default, STR Trim will, actually I'm not sure which side is default, but usually you want both. You specify side equals and then the word both, and that will trim it from the left side of the string and the right side of the string. STR to lower, to upper, and to title, change cases. I honestly have never figured out a difference between to lower and to upper versus to lower and to upper from base R. I'm not sure what STR underscore to lower versus to lower, how they are different. They might be, I don't know. If I were to guess, I would say the STR to lower is more efficient, but changing case is not a very computationally intensive thing, so I don't know. Never tried it. But the thing that's unique to stringer is this to title. That is useful in some contexts if you need to switch everything to title case. And so to title also has a bunch of parameters where you can specify what kind of title case, like sentence case or word case or whatever it is you want to capitalize wherever you want to capitalize it. That can be useful if you're doing things like automatically extracting variable names from one source and then piping those into like a figure or a table. You might want to capitalize stuff and not have to do it by hand. So that's that. Remember, importantly, as we go through all these, by the way, that these all operate on strings. You cannot feed a tibble to a stringer function. They specifically operate on variables, not on tibbles. And when we start combining that with dplyr functions, you'll see why that's important. All right, we've danced around it. Well, we're actually to it now. Full-blown regular expressions. Regular expressions are made much easier by Rebus. If you started looking at the Rebus documentation, you start looking at Rebus, you start to realize that it really simplifies what some really complicated regular expressions look like. This is what is it? Regular expression builder something. Regular expression builder something. Rebus. So what Rebus does is basically takes the regular expression syntax that you see, that you worked in regex1, and it converts it into a much more human-readable format. That is a trade-off, and it's a trade-off you should recognize you are making. Anytime that you sacrifice power for simplicity, you potentially add some weird things along the way. So the regular expression system, the regular expression engine itself, the kind that you learned about in regex1, is extremely powerful and versatile, but it is very hard to read in certain cases. Rebus, in contrast, is much easier to read, but it's also very easy to make a mistake without realizing it. Because Rebus will try to convert what you tell it into regular expression syntax. Sometimes it doesn't actually do it the way you want it to. And I will show you one particular pain point that you are very likely to encounter if you're not careful. So this is Rebus. The quick list you can get in Rebus, this is a really useful thing, is after you call Rebus at least, is that if I do Rebus : you get a quick list of all of the various things that you can call for in Rebus. I mean, this is true of any package, but it's worth remembering for Rebus specifically because it gives you this the full thing right here for you. You can see any car, you can see Arabic characters, you can see Armenian, ASCII, Balkanese, Bengali, block elements, etc. A huge number of constants. I mean, a huge number of constants are included in this thing. And we're only up to B. Byzantine, CJK, don't even know what that is, Cyrillic, day of year, domino, there's our dots that we learned about. You can actually see, there's the end. There's a couple of things that are kind of date time functions, so if you have a date, it'll actually spot it for you. What each of these constants does is it has a type of regular expression that it's associated with. You can actually see it by typing it out. I don't want date time. Maybe I did. Oh, thank you. DYM. This is the regular expression that DYM replaces it with. So that's why Rebus is helpful, so that you don't have to try to figure out how to write this on your own. So that's why you should use Rebus. But I will tell you in a minute what reasons you should not use Rebus, and situations where you should write your own regular expressions instead of bothering with Rebus, and that in turn means places where you can combine Rebus with your own regular expressions, because that's fine too. As long as you use Rebus, though, you need to remember or keep in mind the situation, the fact that you're learning Rebus means you're not learning regular expressions, and if you end up in a kind of job or position where you need a lot of regular expressions, that can be a little bit of a problem, because only R has Rebus. There's no Python Rebus, there's no C Rebus. This is an R package specifically designed to make this easier for R users. So as a result of that, if you learn rebus but don't learn regular expressions and you ever need to use another language for some reason, you may be in a little bit of trouble. Although you could still pull up R and try to convert it to an R regular expression and then try to convert that regular expression into whatever language you need. Because, I will add this caveat, regular expressions are based on an engine and there are different engines. So regular expressions that work in R don't always work the same way in another language. So just keep all that in mind if you ever need to work in other places. When you create regular expressions, scalability is your critical key. I will warn you right now, anytime that I ask you to do regular expressions, I am not going to test them on the data set I gave you. I'm going to test them on a different data set that is constructed the same way. That means that if you do things like create a regular expression that specifically looks for like 3 letters, because those are the 3 letters in that one thing you can't capture that don't work, you won't get credit for that, so don't do that. You need to create scalable solutions that capture most or all of the cases that you're supposed to be capturing. So don't do weird stuff associated with specific cases just to target exclusionary elements. As long as you match what you're supposed to and don't match things you're not, that's what a regular expression does. This is one of the areas where there is so much more flexibility in how you can program that there is no single right answer. There are probably dozens upon dozens of correct answers to most questions using regular expressions. So they're wild west of possibilities. So I don't care what it specifically looks like as long as it matches what it's supposed to. What I do recommend you do is, when you're trying to do this kind of thing, create mini data sets. So like create 7 or 8 cases that are all what you're capturing, but with all of the common exceptions you anticipate in those examples, and then test on that. So in the real world, if you were capturing citations, and I will tell you why I mention that right now. In the real world, if you're capturing citations, they're not always APA formatted, as it turns out. So that means you have to build all sorts of exceptions and weird situations in order to capture incorrectly formatted citations. For your project, you don't have to do that. But if you were actually trying to get citations from websites or pull them down from somewhere, then you would have to do that. So in those cases, you want to create little mini data sets that contain all the boundary conditions, all the slightly weird-looking versions of the thing you're trying to match to make sure that you're actually matching what you're supposed to. This is what regex1 did when it said match these but not these. Those are like mini test data sets that you're working in. Regular expressions are always case-sensitive 100% of the time. Just remember that. Everything has been case-sensitive at this point, but it's worth reiterating here. Meta-characters that are common in regular expressions in base regex, these guys right here. This list on regex1 is actually a really handy quick reference. This is just, if you go to regex1, this is on the right in a little box. It shows all the major different ways that you can format regular expressions. The ones you will use the most often are probably going to be digit, you're going to use character classes, you're going to use word specifications, and you're going to use all these guys down here. Repetitions, optionals, and white space, as well as capture groups. So a lot of these are really very common things that you need in regular expressions in terms of meta characters. An important thing to remember with meta characters, if you were actually looking for a \d in a data set, you would have to escape the backslash, right? Because if you just put a \d, it's going to think you mean digit. What you really mean is a literal, again, \d. So if you're looking for \d literal, you'd have to use \d. That gets weirder in R because \d would be interpreted by the string engine as another backslash. So you would have to do \d if you actually wrote this in R. This is why using rebus is also helpful. Okay. Common constants in the rebus engine, in order to avoid all the problems I was just talking about, alphabetical, alphanumeric, blanks, digits and not digits, lower, upper, punctuations, spaces, not spaces, any characters, and words and not words. This is your core set of meta characters that you use in rebus. Really don't worry about Unicode unless you have a reason to worry about Unicode. There are also a bunch of constants, the ones we just looked through, that are useful, $, parentheses. This namespace document is really useful. One of the things that I just did in a minute ago, I didn't explain it as I was doing it, is I went to the GitHub page for rebus, which is where this is developed and where new versions are being released. Within this, there is a document called namespace, which lists all the things that get exported from rebus into R. So you can get this as kind of a quick list of all of the stuff in Rebus if you need some weird symbol. You will notice it is a very, very long list. So one thing that you might consider doing is if you're looking for something in particular is you might just, use a find in your web browser to see if it's in there. So like if you're looking for quotation marks, you might look for quote, and you might find right there, there's something that looks like a quotation mark but has the word up in front of it, up quotation mark. And then you might create a test data set to see if that's actually capturing quotation marks or something else. Alternatively, you can type that specific phrase back into RStudio, up quotation mark, and see what it ends up putting out. In this case, it looks like set of quotation mark, so you would have to understand what quotation mark represents in raw regular expressions. So yeah, there's a lot of steps there. That's not going to work, right? Yeah. Okay, so let's go back here. There are a bunch of functions here which really represent different versions of a lot of meta characters. And I hope you drew this connection as you were doing it, that a lot of the Rebus functions are really just ways of treating groupings of regular expressions. Character class captures repeated optional 0 or more, 1 or more, negated character class, and exactly, which is really the same as surrounding something with start and end. All of these, in combined with these and literals, is the way that you create regular expressions in Rebus. And for the project, you're going to need to either stitch these together in order to get specific goals accomplished, or have to write it in raw regex, which is, for me, honestly, a little harder. So I would recommend using Rebus and using these pieces right here, but you certainly don't have to. You are able to do it however you want, as long as it works. Common problems with Rebus. Whenever you specify repeating functions, Rebus almost universally assumes you want a character class. That is a profound statement. You probably may not recognize why that's a profound statement. But what a character class does is it treats anything inside it as a literal. So let me show you why that's a bit of a problem. Already do Rebus, and let's do str match strings and any car. That makes sense, right? I'm doing y and u. They're the first characters of each one, so obviously str match matches any car. Okay. Now what happens if I do 1 or more any car? Is that what you expected to happen? Can anybody tell me why that happened? It's weird, isn't it? That's a weird thing to happen. The key is literals. Any guesses? Let me show you how to diagnose this. What happens if I type any car? I actually show the regex, and that is what I would expect. I would expect the dot, right? What happens if I use 1 or more any car? I get a character class for the plus. Remember that the brackets mean character class, so pick any one of the things inside these brackets and then apply what comes after. And again, anything inside a character class is treated as a literal. So this says look for 1 or more literal periods in the text. That's why it broke. Everybody follow that? That's really important. And if you don't understand that, you will be very frustrated on this project. This automatically converted it into a character class, and character classes always treat what's inside them as literals. If I put a meta character inside a character class, it will always be treated as literally that thing. You can override this by saying char class equals false. And that will remove the character class. Which means if I go all the way back up here, and instead of 1 or more any car, I say 1 or more any car char class equals false, now it works. Does everybody see why that happened? You have to check. You can't just trust Rebus to do what you think it's doing, because it guesses in certain situations as to what you mean. So if you're finding that it's not matching what you think it should, it doesn't necessarily mean you're wrong in your Rebus code. It may just mean that Rebus is guessing incorrectly as to what you're trying to do. So pay very close attention. So in this case, car class equals false is how you would fix that problem. Having said that, any car, one or more any car, you almost never want to do. You probably are intuitively going to want to use one or more any car to think, I want any number of characters up until some other character. Don't ever do that. That is not what you want to do. Instead, you want to use a negated class and say any character, any number of characters except the one I'm trying to get up to. So you'll want to say one or more, a negated version of one or more up until like a period, a literal period, up until a parenthesis, up until something, some physical symbol. So you probably, and this is the reason why Rebus guesses that you want a character class, because no one would usually want to do that. So if you start finding that Rebus is guessing incorrectly, it also might point to you not using quite the right approach, or at least not the easiest approach. It might still work, but it might be hard to do. Okay? Double check. I hope we are now past the point where you're just writing code, running it, and if it worked, you move on. Don't do that. You got to check. Develop. Don't write. Okay. Another common error is that Rebus and regex are greedy. By default, they will match as many things as they possibly can. So you probably, and this is the example, you probably don't mean one or more any car, character class, and then dot. If, for example, you were looking for a literal dot, because that's what this does. This does not search for any number of characters until a dot. Why? That's the greedy part. Because there's a dot there, the dot is any character. So it will just continue right on through that dot. And by the time it'll get to the end of the expression, it will say, well, wait a minute, I've hit the end of the expression. Now I need to look for a dot. There's no dot. This will fail. So even if you have text in front of a dot, and that's what you're searching for, all the text until the dot, this will not work, because it will never find that dot. It will greedily match everything there and then give up. There's a way to override this using what's called lazy evaluation, but usually you don't want lazy evaluation. Instead, you want this opposite. One or more of anything that's not a dot. That's usually what you're actually after. Make sense? Regular expressions are one of the more like mind-warping things of doing this kind of coding. So you will fight with regular expressions a lot. This kind of development can, if you get yourself locked into the wrong kind of mental set, this kind of development takes a long time. Because you'll be like, it should work this way. Why doesn't it work this way? And it will never work because you're not doing it the right way. So the key is recognizing when there are situations like this and you really mean something totally different. And it also comes to really understanding how a regular expression engine parses. Captures I talked quite a bit about, but not very explicitly. Capturing returns of pieces of information that's referenced. For example, year, then captured digit, 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 which is really this in regex. Or it could be this if you use repeated. You could also replace these digits with literally the repeated function. All of those are the same. Then capturing returns only the specific piece you want. So in this case, if you had YR colon and then some numbers, it would only return the numbers, because that's the part in the parentheses. STR match returns both the full match and each capture as a new column. So you could have up to like 10, I think, or maybe 9 captures in a single regular expression, and it just makes more and more columns in your STR match. And STR Extract, it just ignores it, as does replace, as does most of those functions. Most of them ignore captures, but STR match will give you back that matrix. Back references can be used to capture things that or to reference things you've already captured. You saw that in DataCamp as the best way to capture repeated information that's variable. So if you want to see the number of times that somebody says the same word twice, for example, you could capture a word followed by ref1. And that would capture any time that somebody types the same word twice. If you use autocorrect in Word, you've experienced that. So if you type the same word twice, like, are you sure you meant to type the same word twice? That's how it's doing it. It's using a regular expression match on your previous characters. So, yeah, back references can be useful that way. For most social science kind of applications, you don't need them most of the time. But it's good to know they exist. Captures, you do need them. Common problems with base regex, and this is I mentioned before. When passing strings as the pattern for a regex, the R string processor will assume your string is a string first, before it ever gets passed to regex. That means if you're using a special character that's in R and regex, you're probably going to need to double escape it. Rebus does help here because Rebus actually creates, and you might have seen it in our examples. You can see right here that this is not returning a string vector. It's returning an object of class regex. The reason for that is to avoid the string processor. That way you don't have to deal with the weird string nonsense. But if you're typing them as plain text, you can't do that. Example. STR detect, this is a sentence, period. What does that do? In string processing, a period is going to be treated as, is not going to be treated as a period. If you try to send this to regex, that period is going to end up getting passed to regex as a plain period, and it will search for any character. But if you actually want to search for a period, it doesn't work. So this is any character. If you search for \period, that won't work either. Because now what you've done is that you've told the string processor this is a literal period in R, so R sends a period, and then when the period gets there, it's still treated as any character. In this case, you are escaping the \, so you end up passing to regex \period. That's what you want if you're trying to capture that period, and this is a sentence. So here, we have to use this expression in order to actually search for \period. Okay? That make sense? It's going through two processors. That's the way to think about it. It's going through first the R string processor, then it's going through the regular expression processor. So it gets done in sequence. In DataCamp, I felt like they kind of hand-waved over this by using this function called fixed. What fixed does is the same thing. It says this is a literal. Just send the literal. So if we send this as a literal to the regular expression engine, now it treats it as a literal period. Okay? The reason that you can't use that most of the time is because you can't combine fixed with other strings, because when you do that, it will coerce the other string. It will convert the fixed into a non-fixed type. So it doesn't work. So if you only need to search for one fixed character, you can use fixed, but there's no other situation where it works. So don't, like you can't concatenate a fixed character with some other regular expression. It has to be literally in there. So you can only use fixed when you're actually searching for literal, period. This is why Rebus is more valuable here, because Rebus will do all of this for you, and it will convert everything into a regex class and then feed that into the regex engine. All right. So the last bit, how do we actually do this in the context of dplyr and magrittr? Again, remember that... I'm going to leave it. Remember that the stringer functions use strings as input and produce strings as output. They do not produce data frames. They do not work the same way dplyr does. Dplyr, part of the advantage of dplyr is it universally takes a tibble, gives back a tibble. String processing doesn't do that. So in a magrittr pipe, you're going to need to use stringer functions as parameters of other verbs. The easiest, most straightforward example here, I'm using the library magrittr just as an example. Again, remember that this symbol right here just means take the existing variable and assign to it the value of this variable plus a pipe. So that's the same as start underscore df pipe start underscore df pipe. Okay? Or start underscore df gets start underscore df pipe. That's the same thing. So this is take start df and assign it the value of start df, and then use the mutate verb to take a new variable called lower text, apply string to lower on an existing text variable, feed that resulting tibble to the next phrase, create a new variable called verb found, and report string match and return column 2. That implies that comma 2 implies that there's a capture inside this pattern. Because remember, the second column is the first capture in a string match. Okay? That familiar? Remember that? If we go back to R, we got an example of it right here. This guy in string match, yes, I put a capture around the Y, so Y comes back as the second column. So the first is always the full match, and then the second, third, fourth, etc. are all of the captures. So if I want to just return the capture, this is the way that you do it in dplyr. I do string match, lower pattern, and then I put bracket, comma, 2. And I also just realized there's a missing closing paren right there. That would be real confusing. So if you're looking at your notes, you should change them. That should be that. So what that's doing is taking string match, lower pattern, then taking column 2 from that matrix, and then assigning that to verb found inside mutate. This is the form that you will use in the project. Okay? That makes sense how that worked? Why that worked? Okay.
Wait, how does it capture if you don't write capture?
Well, this is a variable called pattern, so theoretically we define pattern somewhere else. Yeah. Otherwise, I would have to do it there if that was a string or a rebus expression. And if you don't define pattern elsewhere, you can just literally put a rebus expression there. So you don't need to assign a different variable. So for example, here I could do start y capture. That's a silly thing to do, but I could do something like that. Caps. There we go. So I could do something like literally putting rebus in as a parameter input into this function, and that would give me something like that.